Welcome. In today's video, we're going to derive the mean and variance of the gamma distribution. Before we do that, recall that if x has a gamma distribution, or is distributed with a gamma random variable, with shape parameter alpha and rate parameter beta, then the PDF, or the probability density function of x, is given by the following. F subscript x of x is equal to beta to the alpha over gamma function evaluated at alpha, x to the alpha minus 1, e to the negative beta x, where x is greater than or equal to 0. And recall that our gamma function here has the following definition. It is given by the following integral definition here. It's from 0 to infinity of t alpha minus 1 e to the negative t dt, where t is just some dummy variable. And in certain cases, it's equal to alpha minus 1 factorial, where alpha happens to be an element of the natural numbers. Now that we've gone through just a brief recap of the PDF, we can take a look at the expected value. So the expected value of a gamma random variable, well, it's a continuous distribution, so we're going to use the continuous form of expectation, which is the integral across the entire support of x multiplied by the probability density function of x integrated with respect to x. Now, we know from our previous example above, or our PDF above, that the support of x, or the sample space of x, is for x greater than 0. And so if we look back here, we can write our terminals as 0 to infinity. We've still got our x, and then of course we're going to multiply by the function that we had written above for the PDF. Now, one thing we can do is we can actually do a bit of simplification here. We notice that there's an x here and there's an x here, so we can combine these powers. And I'm going to do that here. This is 0 to infinity of beta to the alpha on gamma of alpha. That becomes x to the alpha plus 1 minus 1 e to the negative beta x dx. And you might be asking, why didn't I just combine the plus 1 and the minus 1 here in the power? And I will go through that in the next step. What I'm importantly going to do here is, in this next step, I'm going to take beta to the alpha over gamma of alpha, and I'm going to relabel this as x to the power of alpha star minus 1 e to the negative beta x dx, where alpha star just happens to be alpha plus 1. And the reason I've done that there is because I want the variables that are dependent on x here on the right-hand side of this function, I want them to continue looking like a gamma distribution, because what I'm going to eventually do here is I'm going to make the whole expression look like a gamma distribution. And this will be a sneaky technique that we're going to use in the integral. So if this were a gamma distribution for a second, I know that I have x to this new parameter alpha minus 1 e to the negative beta x dx. What would I need here at the front of this to complete the distribution? We call this component of the distribution the kernel of the distribution. And I suppose in this sense, the the component that is independent of x, these of course being dependent on x, this is called the scaling factor, I suppose. So what would I need that scaling factor to be? Well, it actually, if we think about this systematically, it needs to look like beta to the alpha star on gamma evaluated at alpha star. Similar to what we have here, except we need new parameters here for alpha star. Now, noting we don't want to change this this distribution or this formula that we have above. So what we're going to have to do is we're still going to have our original beta to the alpha on gamma of alpha. So I've got that beta on alpha to the gamma of alpha here. And then I've got to multiply that by the gamma evaluated alpha star over beta to the alpha star here. That way these components here cancel out with these components here, and we're left back with the beta to the alpha over gamma and alpha that we had originally. Now, why have we done this? Well, we've done this because now we recognize this entire expression here as a new probability density function with with shape parameter alpha star and rate parameter beta. And we know that when we have a probability density function integrated all over the support of itself, then this expression here, that integral, collapses simply to 1 by definition of what the probability density function is, or by the characteristics of a probability density function. So this component here just all collapses to 1. We've still got the starting parameters, so we've still got beta on alpha on gamma of alpha. And now I'm just going to rewrite our alpha star here as instead times alpha plus 1. I'm going to resubstitute in the expression that we had here, alpha star. And then that will be all over beta to the alpha plus 1. And if we do a little bit more simplification here, we're going to use one of the properties of the gamma function. And if you recall, one of the properties of the gamma function, and I'll write it to the side here, is gamma of, say, r is equal to r multiplied by gamma of r, sorry, apologies, it's equal to r minus 1 multiplied by gamma r minus 1. So using this iterative iterative function for the gamma function, what we have now is that gamma of alpha plus 1, well, first I'll rewrite the other expressions, beta to the alpha on gamma of alpha, dot, we've still got beta to the alpha times beta here in the denominator, but what we have in our expression for gamma of alpha plus 1 is we can now rewrite that as alpha times gamma evaluated at alpha. And then this allows us to cancel the beta to the alpha here down with the beta to the alpha here, the gamma of alpha here with the gamma of alpha at the top here, and all we're left with now is just alpha on beta. And this is the definite, or the result for the expected value of a gamma distribution. Let's now derive the expected value of the second moment of a gamma distribution, and this will help us compute the variance of the gamma distribution. So similar to as before, we have the expected value in this case of x squared, which by definition of a continuous random variable is the integral across the support of x of x squared multiplied by the probability density function of x times dx, or sorry, integrated with respect to x. This then becomes, when we substitute in our terminals, 0 to infinity, we've still got our x squared. Then we're going to multiply again by our function gamma of alpha, x to the power of alpha minus 1 e to the negative beta x dx. And similarly, again, what we're going to do is we're going to combine the x squared and the x to the alpha minus 1. Then we've got 0 to infinity of beta to the alpha on gamma of alpha, x to the alpha plus 2 in this case minus 1, e to the negative beta x dx. Again, we're going to use a similar and identical technique, actually, where we're going to label, we're going to have beta to the alpha on gamma to the alpha, x to the alpha, again, I'm going to label it as alpha star minus 1, e to the negative beta x dx, where alpha star is in this case equal to alpha plus 2 in these circumstances. Then again, what I'm going to do is I'm going to apply a scaling factor at the front so that it looks like it will complete the distribution that we've just, or the kernel of this distribution that we've just had a look at. So again, that'll need to be beta to the alpha star on gamma of alpha star, x to the alpha star minus 1 e to the negative beta x dx. And again, we've still got our beta to the alpha on gamma of alpha, multiplied by, in this case, again, gamma of alpha star on beta to the alpha star. So it looks almost identical to how we were doing it before, but in this particular case, again, this component here of the distribution collapses to 1 because this is a probability density function now with a new rate parameter and, new shape parameter and the same rate parameter, just this time the shape parameter is alpha plus 2. So then now what we can do is we're going to have our beta to the alpha on gamma of alpha. Here we're now going to replace our alpha stars in this expression up the top with alpha plus 2, so alpha plus, not alpha plus 1 anymore, but alpha plus 2 over beta to the alpha plus 2. And then, of course, we're just multiplying by the 1 right at the end of this of that integral. Following from this, we're going to use some techniques here. Again, something sort of similar to what we had before, where we expanded this gamma distribution iteratively in terms of its components. So step 1 is to recognize that gamma of alpha plus 2 could be seen as, and actually before I do that, what I will just remind us of is the definition of gamma of r in general uses the recursive formula r minus 1 gamma of r minus 1. So in this particular case, gamma of alpha plus 2 would be alpha plus 2 minus 1, gamma of alpha plus 2 minus 1, which is equal to alpha plus 1 times gamma of alpha plus 1. And then again, we're going to iteratively do the same component again, where we've already established that alpha plus 1 at the front here, and then that gamma of alpha plus 1 simply becomes gamma of, or alpha multiplied by gamma of alpha. So substituting that back into the white text here, we've got, again, beta to the alpha times gamma over gamma of alpha multiplied by alpha plus 1 times alpha times gamma of alpha over, and I'm going to split this denominator of beta to the alpha plus 2 as beta to the alpha times beta to the 2, or beta squared, and then this allows us to cancel this beta to the alpha with the beta to the alpha here, this gamma of alpha with this gamma of alpha here, and all we're simply left with here is now alpha plus 1 multiplied by alpha over beta squared. And so now we can compute the variance of x, which by definition is the expected value of x squared minus the expected value of x all squared, which in this case becomes alpha plus 1 alpha on beta squared minus alpha on beta all squared. And if we continue with the same reasoning here, and I'll move this just to the side here, this then becomes, if we're going to expand the first numerator here, or the numerator in this component, that numerator becomes alpha squared plus alpha on beta squared minus alpha squared on beta squared when we expand this component here, or put the squares through the brackets. And then quite simply, this alpha squared in this side of the equation cancels with the alpha squared at the front, and so we're left with the variance term alpha on beta squared. We're now actually going to look at a more general case, which is simply the nth moment of the distribution, where the distribution is a gamma distribution. And we're going to use again the same technique, but in a more generalized case. So, the expected value of x to the power of n, or the nth moment of x, again we're going to use the continuous definition of the integral. X is an element of the support of x to the power of n multiplied by the probability density function of x, evaluated at x. This then becomes, again, the terminals 0 to infinity, x to the power of n multiplied by beta on alpha to the gamma of alpha, x to the alpha minus 1 e to the negative beta x dx. Then our next step is going to be identical to what we were doing before, 0 to infinity of beta to the alpha on gamma of alpha. In this particular instance, we have x to the alpha plus n minus 1. That's from combining the x to the n here and the x to the alpha minus 1 there. X e to the negative beta x dx, of course, we still have at the back. Again, we're going to relabel beta to the alpha on gamma to the alpha. We're going to relabel this as x to the alpha star minus 1 e to the negative beta x dx. In this case, where alpha star is equal to alpha plus n. Our next stage is then, again, to insert a cleverly chosen scaling factor, minus 1 e to the negative beta x dx, and we've got, again, beta to the alpha on gamma of alpha at the front. We choose a special scaling factor which will make the term inside the integral look like a completed probability density function. That completed probability density function has to look like beta to the alpha star on gamma of alpha star. And then again, we multiply by the reciprocal of the scaling factor that we've just implemented inside the integral. Once again, this integral simply collapses to 1. So then we're left with beta to the alpha on gamma of alpha multiplied by, now I'm going to use the substitution of our A or our alpha star. So putting that into the term gives us gamma of alpha plus n over beta to the alpha plus n. And after some simplification, we know that the beta to the alpha here will cancel with the beta to the alpha here, and we'll actually be left with beta to the power of n out the front. So this whole fraction simplifies to gamma of alpha plus n over gamma of alpha beta to the n. And so this version here is the generalized version of the nth moment of the gamma distribution. I hope this video was informative and helpful. Hope to see you in the next one.